More than a century after it sank, the Titanic is still disappearing, but not in the way most people expect. In warm coastal waters, a steel ship collapses within decades. Wood vanishes within years. Marine life strips everything down to nothing with brutal efficiency. But Titanic exists in a different world entirely, nearly 3,800 meters beneath the North Atlantic, where no sunlight has ever reached, and temperatures hold between 0 and 2 degrees Celsius year after year. The most famous shipwreck in history is decaying at a pace so slow that scientists can only measure change across expeditions separated by decades. And this creates a genuine scientific paradox. Titanic should already be gone. By standard decay models for steel structures at depth, large portions of the wreck should have collapsed long before the 21st century. Yet when researchers descended in 2022 using advanced submersibles, they found railings still standing, hull sections still holding shape, and fragile artifacts resting on sediment far longer than any model would predict. So what is slowing time down around Titanic? The answer is not simply cold water. It is an entire environmental system working in concert: temperature, pressure, oxygen, chemistry, and microbiology, operating at energy limits most organisms cannot survive. Understanding why Titanic is disappearing slowly reveals something far larger than the fate of one ship. It reveals how the deep ocean processes everything humanity has ever lost within it. Temperature is where the story begins, and the physics are more dramatic than most people realize. At Titanic's depth, water holds between 0 and 2 degrees Celsius, with extraordinary consistency across centuries. Unlike surface waters that fluctuate with seasons and storm systems, deep North Atlantic water maintains this near-freezing range with almost no variation across human timescales. Scientists use a measurement called the Q10 temperature coefficient to describe this effect precisely. Many biochemical reaction rates drop by roughly half for every 10 degrees Celsius decrease in temperature. Compared to tropical surface waters averaging 25 degrees Celsius, the near-freezing environment surrounding Titanic slows biological decay processes by a factor of 3 to 10 times. Applied across a century, that multiplier becomes an enormous difference in how much structural material survives. But here is what researchers did not initially expect. When early expedition teams modeled Titanic's decay rate using temperature data alone, their predictions still did not match what they observed on the sea floor. The wreck was surviving even longer than cold water alone should explain. That discrepancy forced scientists to look deeper into the system, and what they found changed how the entire field understands deep ocean decay. The missing variable was dissolved oxygen, and its role in the story is even more decisive than temperature. This is the same principle that explains why food lasts longer in a refrigerator. But Titanic is not refrigerated by any machine. It is placed inside one of the most thermally stable environments on Earth, a natural cryogenic chamber where the cooling system has operated without interruption for millions of years before the ship arrived, and will continue operating for millions of years after the last fragment dissolves. Oxygen controls the speed of destruction in every ocean environment on Earth, and the deep Atlantic delivers it in ways that fundamentally shape what happens to anything resting on the seafloor. Most organisms capable of breaking down organic and inorganic materials depend on aerobic respiration. Without sufficient oxygen, their metabolic efficiency collapses, growth rates fall, reproduction slows, and their capacity to consume and decompose drops dramatically. The deep ocean around Titanic contains dissolved oxygen, but in strictly limited supply. It arrives through the thermohaline circulation system, the massive global conveyor belt that moves cold, dense, oxygen-rich polar water into the deep Atlantic basin over timescales of 200 to 1,000 years per full circulation cycle. Oxygen is not replenished quickly. It is rationed across geological time. This creates what marine scientists describe as an energy-limited ecosystem. Life exists at these depths, far more life than early researchers expected, but every organism operates under strict metabolic constraints. growth is slow, reproduction is slow, consumption is slow. The biological machinery of decay runs at a fraction of the speed it achieves in surface waters, where oxygen is abundant and warm temperatures keep metabolic rates high. And inside this energy-limited environment, the organisms that thrive are not the ones most people imagine when they picture decay. They are not fish, they are not worms. They are microbes, and specifically microbes that have evolved to extract energy not from organic carbon, but from the iron in the ship itself, consuming it one atom at a time in a form of destruction that runs at geological speed and has never once paused since the hull touched the seafloor. When Titanic was rediscovered in 1985 by a team led by Robert Ballard using the remotely operated vehicle Argo, researchers expected corrosion damage consistent with a century of saltwater immersion. What they did not expect were the living structures growing directly from the steel itself. Rusticles. These formations hang from exposed metal surfaces like underwater icicles, some exceeding 1 meter in length. They appear fragile and almost geological in appearance, because inside each one exists a complex microbial ecosystem containing hundreds of distinct species organized into functional communities with internal food webs. In 2010, marine microbiologist Henrietta Mann and her research team identified a key organism central to rusticle formation. Halomonas titanicae, a bacterium specifically evolved to oxidize iron under high pressure, near freezing deep ocean conditions. What shocked investigators further was the scale of the operation. Rusticle communities across the wreck consume an estimated 100 to 400 kilograms of iron per day. Individual rusticles grow at approximately 1 millimeter per year, while exposed steel plates lose measurable thickness at rates of 0.1 to 0.3 millimeters annually across the most heavily colonized sections. Microbial cell densities inside rusticle structures reach up to 10 million cells per cubic centimeter figures, comparable to some of the most biologically productive ecosystems on Earth. Concentrated inside structures most observers would mistake for simple rust formations. Titanic is not corroding. It is being biologically processed by organisms that evolved specifically to exploit the energy locked inside its hull, running a metabolic assembly line that has operated continuously since the morning of April 15, 1912. Pressure at Titanic's depth reaches approximately 37.5 megapascals, roughly 375 times the atmospheric pressure humans experience at sea level. The Titan submersible disaster in 2023 brought its destructive potential into public awareness with horrifying clarity when the vessel imploded catastrophically during its descent to the wreck site. But pressure affects the Titanic wreck itself in ways far more complex than simple crushing force. At extreme pressures, molecular diffusion slows, limiting how quickly corrosive agents can penetrate metal surfaces. Gas bubbles cannot form easily, affecting certain oxidation reactions. Some electrochemical corrosion pathways become less thermodynamically favorable under compression. More importantly, pressure acts as a powerful biological filter that changes which organisms can reach the wreck and how aggressively they can consume it. Many species with gas-filled organs cannot survive at these depths. Large scavenging organisms that could physically dismantle wreckage are mostly absent. In shallower coastal waters, organisms like shipworms bore through wooden hulls and destroy vessels within decades. At Titanic's depth, those biological wrecking crews simply cannot operate. The wreck exists in a zone where the same extreme pressure that contributed to its violent structural failure during the sinking now paradoxically slows its surface destruction. An irony the ocean does not acknowledge but science cannot ignore. The deep ocean is commonly imagined as absolutely still, but deep water moves slowly, subtly, shaped by planetary physics operating at scales that dwarf human observation. At Titanic's depth, bottom currents typically flow at 1 to 5 centimeters per second, transporting fine particles in a constant downward drift. Scientists call marine snow a mixture of dead plankton, mineral dust, and microscopic shell fragments from surface organisms far above. Over more than a century, this material has settled unevenly across the wreck. Some surfaces are partially buried, others remain exposed to full current flow. This creates profoundly different decay environments, separated by only a few meters of distance. Buried sections experience lower oxygen exposure, reduced bacterial colonization, and slower corrosion. Exposed sections receive more oxygen, more microbial contact, and deteriorate faster. The result is a wreck, dissolving not uniformly but according to its own invisible geography, a pattern scientists have documented through photographic comparisons across expeditions spanning 4 decades. Structural weakness has accelerated in areas already mechanically stressed during the sinking. Computer modeling suggests major recognizable features could collapse beyond recognition within the next 50 to 100 years, not through sudden catastrophic failure, but through the slow accumulation of millimeter-scale losses finally reaching the threshold where structural integrity gives way entirely, which raises the deepest scientific question the wreck offers. If cold water slows decay so dramatically, why will Titanic still inevitably vanish? If the exterior of Titanic is disappearing slowly, what is happening inside the hull may be even more scientifically remarkable, because Titanic is not decaying as a single unified structure. It is decaying as hundreds of separate microenvironments, each following slightly different chemical and biological rules depending on the specific conditions inside individual compartments. When the ship broke apart and both sections struck the seafloor, the violence of impact sealed many internal spaces behind collapsed bulkheads, debris piles, and drifting sediment. Water circulation inside them slowed dramatically. In compartments where oxygen was consumed and not replenished, microbial communities slowed dramatically, and materials survived far longer than exterior sections exposed to continuous current flow. In other compartments where hull damage allowed slow water exchange, iron-oxidizing bacteria continued feeding and decay accelerated. The wreck is dissolving in a mosaic pattern driven entirely by the invisible geography of its internal structure. The materials inside tell their own chronology. Wooden furniture has largely vanished, paper dissolved within years, textiles have reduced to fiber traces. But glass bottles remain structurally intact because silica resists dissolution at near-freezing temperatures. Ceramic dishware survives because fired clay is chemically inert in seawater. Some leather items have persisted in compartments where oxygen levels dropped low enough to suppress bacterial metabolism. Copper alloy objects resist the specific bacteria that consume iron and corrode through different, slower chemical pathways than steel. Where marine snow drifted inside through openings over decades and partially buried objects on interior floors, that sediment layer functions as a protective blanket, limiting oxygen contact and microbial access, slowing degradation, further accidentally preserving some artifacts longer than objects sitting in open water just meters away. The grand staircase is gone, its wooden structure consumed, its volume now an open cavity filling slowly with rust particles, sediment, and biological material produced by microbial communities colonizing every available surface. The space that once defined luxury ocean travel has become part of the seafloor. Rooms have become cavities. Corridors have become sediment channels. Cabins have become microbial habitats. Structure has become geology. Engineering has become seafloor. And the most important scientific questions are no longer about what Titanic looked like in 1912, but about what is happening inside those sealed dark compartments at this exact moment. Nothing in the ocean escapes recycling. Not steel, not wood, not the atoms that once formed the hull plates assembled in the shipyards of Belfast in 1911. Iron-oxidizing bacteria continue consuming exposed steel at rates scientists estimate could eliminate most recognizable metal structure within 200 to 300 years of the sinking. To grasp what that timescale truly means in the time it takes a major city to rise, transform beyond recognition, and be largely forgotten by history, Titanic loses only centimeters of steel. In the time it takes a civilization to collapse and be replaced by another, the wreck loses a structural beam. The ocean does not operate in human time. It operates in geological time, and Titanic is currently living inside that difference, demonstrating it with every millimeter of steel that dissolves into the water column. Titanic represents the longest continuously monitored deep ocean decay experiment available to science. Expeditions in 1985, 1986, 1991, 1995, 2001, 2004, 2010, and 2022 have documented progressive structural loss across nearly 4 decades of direct observation. Each return reveals changes invisible to previous visits: collapsed decks, expanding rusticle fields, slow disappearance measured in millimeters per year across a structure that once measured 269 meters in length. Less than 0.0001% of the abyssal seafloor has ever been directly observed by human or robotic systems. Titanic is one of the most studied points in that vast, unmapped darkness, and what it reveals about microbial ecosystems, pressure chemistry, and long-time-scale material transformation is actively reshaping how researchers design experiments across the entire field of deep ocean science. Climate change enters almost no public discussion about deep shipwrecks. It feels counterintuitive these sites exist so far below the surface that surface events seem impossibly distant. But scientists studying deep ocean systems are increasingly attentive to how planetary scale changes propagate into the abyssal environment, and Titanic exists on exactly the timescales where those changes become relevant. Deep ocean temperatures change slowly, but they do change. Ocean heat content measurements across the Atlantic basin show that warming signals from the surface are gradually penetrating into intermediate and deep water layers. Even temperature increases of 0.1 to 0.5 degrees Celsius at depth changes, invisible to human perception, can meaningfully shift microbial metabolic rates over decadal timescales. If the Q10 temperature relationship holds at these low temperature ranges, even a fraction of a degree warming could measurably accelerate iron oxidizing bacterial activity and increase overall corrosion rates across the entire wreck. Changes to thermohaline circulation patterns, driven by freshwater injection from melting polar ice, could alter how quickly oxygen-rich water reaches Titanic's depth. Increased or decreased oxygen supply would directly change the biological activity ceiling of the microbial ecosystem consuming the ship. None of these changes will accelerate Titanic's disappearance in any time frame a living human would observe. But Titanic will exist for another century or two, and the cumulative effect of even gradual environmental shifts across that duration is not negligible. Scientists are beginning to consider the wreck as a passive environmental monitor, a site where long-term corrosion rate measurements could eventually reveal information about deep ocean condition changes that would otherwise require expensive instrumentation campaigns to detect directly. The ship that humanity lost is quietly becoming an instrument science uses to understand the planet. Titanic demonstrates a fundamental truth about the deep ocean that took decades of direct observation to fully appreciate, and that still rarely reaches public understanding of what these environments actually are. The deep sea is not a place of rapid destruction. It is a place of slow transformation, and the distinction matters enormously. Cold water slows the chemistry of corrosion. Limited oxygen slows the biology of decay. Extreme pressure filters out the most destructive biological agents. Low available energy stretches every metabolic process across timescales that feel almost geological to organisms living at the surface. These factors do not prevent Titanic from disappearing. They simply change the speed, the sequence, and the pathway by which it disappears. Steel becomes dissolved ferrous ions entering the water column. Those ions feed the iron-oxidizing bacteria colonizing every exposed surface. The bacteria support rusticle ecosystems containing hundreds of species across multiple trophic levels. Those ecosystems produce organic carbon that feeds other microbial communities. Those communities become part of the local deep ocean carbon cycle, which connects upward through the water column to surface productivity and ultimately to the global carbon cycle, regulating Earth's atmosphere. Titanic is not just corroding, it is being converted, element by element, into the chemical and biological fabric of the ocean itself. The ocean does not forget what sinks into it. It transforms everything into something it can use, on timescales that make human history look brief. More than 100 years after it sank, Titanic remains one of the most scientifically important sites in the deep ocean, not because of the history attached to it, but because of what it has revealed about environments humans are only beginning to understand. Cold water did not save Titanic. Nothing saved it. What cold water did was slow the process enough for science to observe, document, and begin to comprehend what the deep ocean actually does to everything that reaches it. One day, the railings will fall, the decks will collapse. The outline that once defined the most famous ship in the history of human seafaring will dissolve into sediment and chemistry. And when that happens, it will not be an ending. It will be the completion of a transformation that began the moment the hull touched the seafloor on the morning of the 15th of April, 1912. Because nothing truly disappears in the ocean. Atoms from Titanic's steel are already cycling through deep-sea chemistry, already incorporated into bacterial cell walls, already dissolved into the water column, and participating in processes that will continue across timescales longer than human civilization has existed. Titanic is not dying. It is being absorbed into Earth, converted, element by element, into the ocean itself. If you find yourself drawn to these hidden processes, the physics of extreme pressure, the biology of total darkness, the slow transformation of human history into planetary chemistry, then you are already exploring what sunken realms deep exists to uncover. Because the deepest parts of Earth are not empty places, they are places where time moves slowly enough for science to finally see how our planet really works. And sometimes, the greatest mysteries are not about what was lost in the ocean, but about what the ocean is, quietly, patiently, and permanently turning them into.